Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm Associate Professor in the Stewart School of Industrial System Engineering. This lecture is on basics of time series analysis, and for this lesson, I will focus on the concept of stationarity. Let's first define the autocovariance function. The autocovariance function is the covariance of any two variables of the stochastic process. For example, if we consider the time points r and x, the autocovariance of xr and xs is the expectation of the product of the mean-centered variables xr and xs as provided on the slide. Further, we define a time series xt to be weakly stationary if it has constant mean for all time points t, it has a finite variance, or more specifically, has a finite second moment, and the covariance function does not change when shifted in time. That is, the dependence between xr and xs is the same as for the shifted xr plus t and xs plus t. Two classic examples of stationary processes are the white noise process and the IID process. A white noise process xt has constant variance, sigma squared, uncorrelated, and constant mean equal to 0. The IID process has constant variance, independence, and constant mean equal to 0. Both are stationary since the conditions 1, 2, 3 hold, assuming that sigma squared is finite. As the two processes are defined on the slide, it may seem that they are actually the same. What is the difference? The white noise process assumed uncorrelated data. That means xt are uncorrelated, whereas the IID process assumes independence. Independence implies uncorrelated variables, but not the opposite. Thus, it is possible to have uncorrelated variables, but not independent. How to sample such processes in R? We can use the random generator for the normal distribution, R norm, for example, if we're interested in random normal data. For other distributions, we can use R poise for the Poisson distribution, R binom for the binomial distribution, and so on. This is the time series plot obtained for white noise with 0 mean and variance equal to 1, obtained using the R function R norm. A classic example of a non-stationary process is the so-called random walk. For a random walk, we start with an IID normally distributed random variables xt with mean 0 and variance sigma squared. A random walk process st is the sum of xt's up to time t. Here is the plot of one random walk. As you noted from this plot, there is not stationarity in this process since it goes up and down differently across a time span and thus with a different distribution as the process shifts over time. Another example is the moving average of order 1, which I'll introduce in more detail in a different lecture. This process is not stationary for some specific values of data. One example is in this plot. Comparing to the previous example, stationarity is not so clearly identified in this example. For a stationary process, the autocovariance function does not change as time shifts. Thus, we can express the autocovariance function in terms of the lag rather than time. Specifically, for a stationary time series, the autocovariance function is a function of the lag h is the covariance of xt and xt plus h. The autocovariance function has the following properties. The autocovariance function at lag 0, which is the variance of xt, is positive. This is because the variance is positive. The absolute value of the autocovariance function at lag h is bounded above by the variance or the autocovariance function in 0. Last, the autocovariance function in the lag h is equal to the autocovariance function in the lag minus h, hence it's symmetric. This last property comes from the fact that the distribution does not change if shifted a lag h before or after a given time point. We can further define the autocorrelation function of a stationary process xt as the scaled autocovariance function. We divide the autocovariance function in h with the autocovariance function in 0. Because of this rescaling, the autocorrelation function has the addition property that evaluated as 0 is equal to 1. The autocovariance and autocorrelation functions are functions of the stochastic process xt and thus are unknown. We can obtain estimate of these functions given the realizations or observations of the time series. Specifically, given the observations of the time series x1 to xn, we estimate using the sample autocovariance and sample autocorrelation functions. The sample autocovariance function at h is the sum of the products between any two mean-centered observations of the time series observed within a lag h. The formula is provided on the slide. The sample autocorrelation is simply the sample autocovariance divided by the sample autocovariance at 0. To summarize in this lesson, I provided the basic concept of stationarity. Thank you. Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm associate professor in the Stewart School of Industrial System Engineering. The lecture is Basics of Time Series Analysis, and in this lecture I'll focus on stationarity with a data example. We'll return once more to the data example where we're interested in modeling monthly average of the temperature in Atlanta. We have seen so far how to estimate the trend and the seasonality. We'll take a closer look at the stationarity of the residual process after removing those two components. The general approach for a time series analysis is as follows. We first begin with an exploratory analysis for insights on whether the time series is already stationary or whether there is a trend and/or seasonality to account for in the modeling of the time series. We also look for other aspects such as outliers or unusual patterns. If trend and/or seasonality are present, then we can estimate them and remove them from the observed time series. Next, the residual process is checked for stationarity, and if it's stationary, the time series model is further employed. So far, I illustrated steps 1 and 2 for the analysis of the monthly average temperature. Next, we'll study the stationarity of the residual process. I'm showing you this residual process again. This is comparing the residuals from fitting both the trend and seasonality using the two approaches, the linear regression model and non-parametric regression model. The question that we'd like to answer is this residual process stationary? A stationary process is described by the behavior of its autocovariance or autocorrelation function. So let's look at the sample autocorrelation function for the residual plots from the two approaches. The R command is ACF, which allows estimation of both the autocovariance and autocorrelation functions. The default of the R command is the autocorrelation. We're plotting here the ACF for both the temperature time series process and the residual processes after removing the trend and seasonality using the two approaches. A stationary process is described by the behavior of its autocovariance or autocorrelation function. Let's look at the sample autocorrelation for the residual plots from the two approaches. The R command is ACF, which allows estimation of both the autocovariance and autocorrelation, the sample autocovariance and autocorrelation functions. The default of the R command is autocorrelation. We're plotting here the ACF for both the temperature time series process and the residual process obtained after removing trend and seasonality using both approaches discussed before. The ACF plot of the temperature process is here. The x-axis shows the lag age at which we estimate the autocorrelation function, and the y-axis is for the sample autocorrelation. The ACF plot shows a clear seasonality pattern. The pattern repeats for each block of lags specified at 1, 2, 3, and 4 on the y-axis, on the x-axis. The trend cannot be noted from this plot, cannot be observed from this plot, since it's slowly changing over years, as we have seen in the lesson where we learned about the trend estimation for this particular time series. The ACF plot of the residuals from the parametric approach for estimating the trend and seasonality is here. While the seasonality observed in the ACF of the temperature time series is not present anymore, we still observe some sort of cyclical pattern that corresponds to the periodicity of the time series. Moreover, most of the ACF values are positive, showing some bias in the estimation of trend and/or cyclical pattern. Last is the ACF plot for the residuals, where the trend is estimated using non-parametric regression. The ACF plot for this residual plot does not have a cyclical pattern of the ACF plot of the previous residual plot, and it shows less of the bias in the removal of the trend and/or cyclical pattern. However, none of these observations about the residual plots guarantee stationarity. We'll expand more on this aspect in a different lecture. To summarize, in this lesson, I provided an overview of how to evaluate stationarity using a data example. Thank you. Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm Associate Professor in the Stewart School of Industry and System Engineering. This lecture is on basics of time series analysis. And for this lesson, we'll learn about the definition of linear process and prediction. A time series is a linear process if it can be represented as a linear combination of a white noise process where the coefficients in the linear combination have the property that the sum of their absolute values is finite. A special case is the moving average process in which all the coefficients with a negative index are 0. Most models discussed in this course are linear processes, or they can be expressed as linear processes under specific conditions. In all models, however, the processes are finite sums. An example of a linear process is the autoregression, in short AR process, with a one order expressed as xt equal to phi times xt minus 1 plus a white noise process zt. Comparing this formula with that from previous slide, there is not a clear mapping between them. But it can be shown using some algebra that the AR with one order is a linear process if the coefficient phi in absolute value is smaller than 1 and the white noise process zt is uncorrelated with the process xs before the time point t. An example of an AR process of order 1 with phi equal to 0.8 is provided here. For linear processes, as provided in this course, and more generally for stationary processes, we'll particularly focus on one type of prediction, linear predictors, which are linear combinations of past data. We define the prediction at lag age, given the past n observations, as the linear combination of the n past data, with different weights provided for the more recent data versus the older data. Here, the coefficient A1 is for the most recent data of the time series. Xn, A2 is for the next recent data for the times of the time series Xn minus 1, and so on. In order to get the coefficients A1, A2 to An, we minimize the mean squared error with respect to these coefficients, which will define the best linear predictor. In prediction of stationarity processes, our goal is to obtain best linear predictors. This slide provides the notation that will be used in the prediction based on models introduced in this course. Again, we begin with a stationary process with mean mu. The best linear predictor is expressed in terms of the linear combination of the past data centered around the mean mu, if mu is not 0. This formulation is equivalent with the one provided on the previous slide, except that we now express the constant A0 in a previous slide in terms of mu. Here, I define alpha n as the vector of coefficients in the linear combination of the past data, in the linear combination for the prediction. The coefficients in alpha n are directly related to the autocovariance function of the time series through this equation. In this equation, gamma n is a matrix where the ij elements in this matrix are the autocovariance functions at I minus j. Gamma n times the vector of coefficients is equal to the vector gamma n at h. The prediction error, which is a measure of accuracy of the prediction, can be further obtained once we have the coefficients in the alpha n vector. Let's consider the very simple one-step prediction, that is, predict xn plus 1 from the past data of the time series x1 to xn. If the matrix gamma n is non-singular, then we can obtain the coefficients in the alpha n vector by multiplying both sides with the inverse of gamma n. Once we obtain alpha n, we can get the prediction and the prediction error. But gamma n minus 1 can be too large to invert for n large. There are two common recursive algorithms that can be used instead of inverting this large matrix, and those recursive algorithms will give us directly the predictions. The first algorithm is a Durbin-Leveson algorithm. In this algorithm, we're getting the coefficients in the alpha n vector to be used to obtain the prediction and the prediction error. This algorithm does not require the inversion of the matrix gamma n, but will require getting the coefficients in the alpha 1, alpha n, and so on, all the vectors up to alpha n vectors recursively. In the second algorithm, called also the innovations algorithm, we do not obtain the coefficients in the alpha n vector, but we're getting directly the predictions. In this algorithm, we first compute the elements of the K matrix, in which the ij element is the expectation of xi and xj. This is one-time computation. Then we get the one-step prediction using a formula involving the weighted sum of the differences between past data, xn plus 1 minus j, and their prediction, and those are called also innovations, hence the name of the algorithm. The weights are the theta and j, which are functions of the elements in the K matrix. In summary, in this lesson, I provided the concept of linear processes and their implications in prediction. Thank you.